Welcome to Krishna's classes. Last time we proved a version of the fixed point theorem in a complete metric space. Now we discuss some applications of this theorem because it's a very important result, especially in getting the solutions of certain types of equations. Now, one of them is the celebrated existence and uniqueness theorem in ordinary differential equations. This dates back to the 19th century when Picard's approximation method was used to prove the existence of the solution, or at least to compute or get a good approximation to a solution. Now let us recall the problem. So consider the ODE. The ordinary differential equation y derivative equal to where xy belongs to D part of R. D is assumed to be open and connected. Let belong to D. And consider the initial value problem. We make some statement about the make some statement about f. We assume let continues. Let x naught y naught belong to D. Consider the initial value problem IVP y derivative f of xy Let me denote this by 1. So this is the initial value. Now the problem is to find a solution of 1 that is a continuous function with continuous derivative on some interval AB containing x0 and such that y derivative of x yx and y0. This is what we mean by a solution of the initial value problem. What we are looking for is this. Does there exist a solution for the initial value problem? Under what conditions that means give some sufficient conditions under which the solution is uniquely determined. So these are the this is the central question that we are addressing in this lecture, and we use the fixed point theorem as a tool to establish this. Okay. Now, remark in general, you need some further restrictions F. So further restrictions on F. to assert the uniqueness of the solution. To establish the solution. So let us introduce one such condition, Lipschitz condition. F is Lipschitz with respect to y on D with a Lipschitz constant L if for every x y1 comma in D or L is called the Lipschitz constant. Now we shall not digest too much on this because that's a totally different direction in which we will be discussing this, and there are details of this, some conditions under which Lipschitz condition is assured, etc., etc. It is all available in the literature. Now in this talk we assume F is Lipschitz with this condition. So let me write down, often use 2 to recall this. So we start with the assumption as given in 1 along with the further assumption that F is Lipschitz with respect to now the strategy which is very often done in mathematics to solve such problems is, if you cannot directly solve it, you transform this problem into another problem which is equivalent to it. So we shall transform this problem into another problem. So an integral equation equivalent to the IVP1. So let us convert this problem into an integral. IVP, an integral equation. Which is equivalent to 1, the initial value problem 1, in the sense that all solutions of the IVP are solutions of the integral equation and vice versa. That means instead of solving one, we find solutions of the integral equation, then it automatically becomes a solution of the initial value problem. Because the way in which we transform this, it follows that every solution of the integral equation is a solution of the initial value problem, and every solution of the initial value problem is a solution of the integral equation. So let us do this. So we use the following. Okay. Let y of x then or I will use then we have psi derivative of x equal to f of x for every x belonging to AB. Now you see that being a solution of the integral equation, psi is a differentiable function and f being continuous in both the variables, since psi is continuous, you see that fx psi x is a continuous function, therefore psi derivative is also continuous. Okay, so note that is continuous. Now let us integrate this on both sides from 0 to x. Now integrate this from 0 to x. Both sides let me designate this by 3 over x naught belong to AB we have integral x naught to x psi derivative of t dt equal to integral x naught to x f t psi t dt. Now for x belonging to m. Now this would give you now psi x naught equal to y naught, hence we have now this implies the following. This implies is a solution of the integral equation. Is a solution of the integral equation y x equal to dt. Conversely, if y equal to psi x is a solution of integral equation 4, then by differentiating on both sides, we have y and y x naught equal to every solution of four is a solution. That means instead of solving one, it is enough to show that there exists a solution for the integral equation. To it is sufficient to show that 4 has a solution. So, instead of the initial value problem, now we work on the integral equation. Therefore, it is enough to show that the integral equation has a solution. Let us look at this problem. Okay. So, what do we have to do? We have to show that, see, the problem is this. So, we show that there is some interval containing x naught on which a solution of the initial value problem exists, or equivalently a solution of the equivalent integral equation exists. Okay. So, this is what we are up to. So, we have to fix a interval on which we show that this integral equation has a solution. That's our task. And indeed, what we are doing is, because I will be digressing into differential equations then, but still I will just make some remarks here. We prove that in some neighborhood of x naught, under the conditions on f, there exists a unique solution of the initial value problem. Okay? And which is equivalent to proving that on some interval containing x naught, there exists a unique solution of the equivalent integral. Okay? So we are only proving the existence of a local solution. That means we are saying in some neighborhood of x naught, and there are ways of extending it to the whole interval under conditions and so on. All this is a different story altogether, because we will be losing our focus there. Our focus is how do we exploit the fundamental result, that is the fixed point theorem, to come to our conclusion. So the problem is, how do we use? So what we are after is this: how do we use make use of the fixed point theorem in solving this in establishing this the existence of a solution. That's our task. So we have to reformulate the problem in the language of the fixed point theorem. What was the language of the fixed point theorem? Just briefly recall the fixed point theorem. It's very general. Let a complete metric space let P be from x into x be a contraction. Then there exists a unique solution there exists a unique x belonging to x such that is there exists a unique fixed point T in x. So that is the theorem that we are going to make use of. So we have to convert this problem into that language. Okay. So let us do that now. So we shall choose a delta. Let us consider such that x naught minus delta is contained in the we have not, we shall fix this according to our requirement. And observe that x defined by as a set of all continuous functions on x naught minus delta with sup norm is a complete metric space. Because once you have the supreme norm, in fact it's a complete normed linear space. And hence a complete metric space. So we have identified a possible complete metric space. Now we have to set up the map T from x to x. Okay. Let us now, okay, define T from x to x and show that it is a contract. Then T has a unique fixed point. That means in X. Then T has a unique fixed point in X. Now this T has to be related to equation 4, the integral equation 4. Then only and shall be such that its fixed point is a solution of so how to work out the T? Therefore, definition of T. Or construction of T. Define, what we do is shall dt. So this is the definition. Okay. In such a way that T maps into is a contraction. T maps this into this, and T is a contraction. How do we choose delta positive? This is what we have to be careful about. So we make the choice, and you can see how this choice turns out to be, how this particular choice comes about, that we shall see. Now, we choose delta to be one is less than 1, 2 is contained in D in some rectangle of the form contained in which is contained in D, where mod on let us examine what it is. See, you have D is some, it may be bounded or unbounded, we don't know. But all that we assume it is open connected. Now x naught y naught is a point of D. Now what we do is, we first choose a rectangle here. We choose a rectangle here such that this point is this distance is A and this distance is B. Okay. Now it's a closed, it's a compact subset. So let us call this R. Okay. Well, now what do we do? On R, Now you see on R, F is bounded. The reason is R is compact and F is continuous. Let M be such that mod F of less than or equal to M. Such an M exists. There is no problem. So that's about M. And what have we chosen? We have chosen now delta. We choose less than 1. And x naught minus delta the point R in the rectangle R. Okay, so we make this choice. Therefore, since R is contained in B, you see that this is contained in D. Okay, let us now examine what type of operator is this. Now, T Y we have defined it as therefore, let us work out this. So, this is a function. How far is this function from y naught, this line? This is what we are estimating. dt, and this you see is less than or equal to this is bounded by M mod x minus x naught, and mod x minus x naught we are taking because x belongs to so this estimate is there. Okay. Therefore, how have we chosen M? See, this is in R. Therefore, This is is less than m delta, which implies T is a map from X into X. X into X. Because you see that it maps the point x naught minus delta to x naught plus delta into this. Okay. So T maps x into x. Look at the definition of x, then it will be clear. And even this picture or this figure should enlighten you on this aspect. Because a lot of things have to be put together, and you see that this is less than m delta. Therefore, you see that Tx, so this implies Ty belongs to this is what we, therefore T maps from X to X. So T is mapping elements in X into X itself. One condition is satisfied. Further, we have T of this is equal to integral of T2. This is what you have, because that why not get cancelled in your never look at the definition of T, and we apply Lipschitz condition. This is less than or equal to mod integral we have applied the Lipschitz condition here. So this part is less than or equal to L times this. So we just replace that. And that means the following. You have supremum of this. That means norm of Ty1 is less than or equal to, this part will come out as norm you take supremum on both sides, take that inside, so on, times this the mod x minus x naught is less than delta. What does it mean? And you see that This is how this condition comes. Choice of this condition comes. Which in turn implies strictly less than norm of y1 minus. Thus, T is a contraction. So T maps a set of all continuous functions x0 minus delta with sup norm into the same class infinity, which is a complete metric space, and T is a contraction. What does it mean? This implies, by applying the X-point theorem, there exists a unique function y of x belonging to delta such that T of yx equal to y. That is okay. Now, what is the consequence of that? It's the integral equation a unique solution delta x0 minus delta to x0 minus delta. Or equivalently, on the initial value problem as number delta I is less than 1. Now this completes the proof. So that proves the theorem. So the important part is to demonstrate how one makes use of the fixed point theorem to obtain or to solve one of the cornerstone theorems in the theory of ordinary differential equation. Thank you very much.